That was fast. All right, good morning, everybody. So we start our day today with the second lecture by Luna about jets.
So, yes, so let's see. Yeah, so yesterday I was mostly talking about heavy ion physics. And for the second part today, it will be mostly about jets and how we use jets to study different things. And this is a very big topic. So as usual, the disclaimer, I cannot possibly go through everything. So what I'm trying to do here is to give you some flavor of what are the things, how they look like, and how they come to be, and how people are using it. Just a kind of a introduction to the subject. And if you're interested in any of those, I'm happy to discuss more afterwards. Invite me. Okay, so there will be roughly two parts. First, we will talk about how jets look like. Just give a mental image, and then some application of jets, what we can learn about it. Okay, so before I go to jets in different places, let's first talk about jets in vacuum, because this is the simplest case. So what are jets? Suppose we have some collision, and then we knock out a highly virtual parton. The parton is called gluon, and it carries a high virtuality Q square. Okay, and this Q square essentially is, in layman terms, kind of how violent the collision is. A little bit more precise term is it's highly virtual, means that the energy momentum relation is highly imbalanced. So if you calculate E square minus P square, it will not be rest mass squared. It will be some other number. And the difference of this shows you how off-shell it is. Okay, and because it's very off-shell, remember the uncertainty principle, there's delta E times delta T. So when we have large delta E, we will have small delta T. So it cannot exist for a long time. Therefore, it will want to split in order to reduce the virtuality. Okay. And so the result is that if you initially have a high energy quark gluon, you will repeatedly split to reduce virtuality, and it will develop into a spray of particles. Okay. And this spray of particle is what we call a jet. Okay. And experimentally, jets are essentially a proxy for the initial particle. So when we see a tightly packed jets, we know that there's probably a quark in the beginning, and we can use this group to study the property of it. Okay, so that's the basic idea. And this is some example of how it looks like. So this is E plus E minus data from Aleph collaboration during lab times. So on the left here, each line is a particle, charged particle, and the length is the momentum of the particle. And we can see that there are two groups of particles. So this is a two-jet event. Okay, so there's one here, one here. Okay, and here is an example a bit more complicated. There are 4 visible jets plus some other random particles around. Okay, so this is how it looks like. And now let's look a little bit more closer at how they look like and how can we understand it. So to model it, people use something called the parton shower. Okay. So the parton shower refers to a process where you have an initial particle gluon, and then it develops a bunch of particles. So this process is parton shower, the showers. And this is a key ingredient to model almost everything. As long as you have a quark or gluon final states, you will have jets. And to gain a little more insight, we can look at one example of the cross section. So in this case, we're looking at E plus E minus 2 R gluon. Okay, and the cross section can be roughly written as this form. So this is the dominant term. So the 3-particle cross section is roughly 2-particle cross section. So just the Q bar part times some extra term that describe the splitting. Okay, and you notice there are 2 variables here. One is the splitting opening angle theta, and also the z, which is the momentum carried by the softer gluon. Okay, and from this, if you look at this form, we can already learn something very interesting about jets, which is that it's both collinear divergent and self-divergent. Okay, so when theta goes to 0, it diverges. Also, when z goes to 0, it diverges. So this means that this will be dominated by the cases where the splitting is collinear, and also when this gluon is very soft. Okay, and this essentially tells us one important thing about the jets, which is that we expect that jets will have a lot of collinear splitting and a lot of soft splittings. Okay, and this explains why we in experiments, when we have spiral particles, it's always very tight. And that's a consequence of this kind of thing. So this is just a special case, but you can also work out different combinations. And the general conclusion is the same. Okay, and because of time, I will not go into too much math, but I will just do a quick sketch of how we simulate a parton shower, because I think it's instructional to know how it works behind the hood. So suppose we want to build some simulation and we want to simulate the process. Okay, and yeah, so in the beginning, we have some parton with some virtuality Q squared, Q naught squared, and then at some point it splits. Okay, and so how do we model this thing? So the strategy is we build emission probabilities using cross sections. So we have to go back. We have to, for example, we can write a 3-body cross section, a 2-body cross section times something else, and that's something else we can build the emission probability on. Okay. And once we build the emission probabilities, another thing we have to do is we have to pick an ordinary variable to evolve things. And there are many choices. For example, we can choose virtuality. That's one choice. Or we can choose angle. That's another popular choice, and so on. And in this example, let's use virtuality. Okay. So the meaning of this is that we will start the parton from some scale in virtuality, and then you will go down step by step until the hybridization scale. And the showering process, we will go through this step by step, one by one. Okay, so in this case, we have a Q naught. We made it to have a Q squared and something, and then the Q squared, the child's parton has a lower virtuality. It splits lowered, and then you will keep going. So the way you build things is that you build something called the first emission probability. So the probability of this thing happening is a product of 2 things. First, there's an emission at Q squared. And then there's a probability that it doesn't emit between here and here. Okay, and this is usually called the Sulaco form factor. It has many other uses in theory, but let's not go into it for now. And once you have these, you have the probability, and then all you have to do is throw dice. Yeah, so you throw a dice to determine where it splits, and then you throw another dice to keep going, and then you develop all the shower. So this is roughly the roadmap of how, like if you run PDL, this is what's doing behind the hood. And obviously I skipped a lot of math here. So if you're interested, I can point you to the math. But yeah, here I'm just telling you the story of how things go. And one thing I want to emphasize is that there is a choice of ordinary variable in this process. So we have to choose some variable to evolve things from. And yeah, so for example, angular order is another popular choice. In this case, when you split things, large angle splits first, and then subsequently you split into smaller and smaller angle. And virtuality is, well, another obvious choice. There is also transform momentum and so on and so forth. And the bottom line is that these are choices, okay? And depending on your choice, they give different shower history. So when you have a quark evolve into a bunch of partons, and exactly how you connect the lines will differ depending on what your choices are. But in vacuum, this doesn't really matter as long as you do things self-consistent and you take care of some of the small issues based on your choice. Okay, so that's in vacuum, and the reason I'm bringing this up is that when you have quark-gluon plasma in heavy ion, this actually matters because there's quark-gluon plasma evolving around it. So which one goes first, which one goes second, actually will matter, but in vacuum it doesn't matter. It's just as long as you do things self-consistently, it's okay. Okay, so then let's move on to the next subtopic, which is how do we find jets in experiments? Okay. So far we described that we have a parton, we develop a bunch of particles, and then all these particles we call jets. Okay, but in experiments things are a little bit more complicated. So the reason for that is that we don't know what comes from what. So suppose we have some collision, then you have a bunch of particles. We don't know which ones are from the initial quark, say. And therefore, we use some algorithm to define our jets. And those algorithms are called the clustering algorithm. And throughout the year, there are many algorithms. And recently, the one class of algorithm that's more popular is called the sequential recombination algorithm. It's essentially a kind of greedy algorithm. So it goes like this. So suppose you have a bunch of particles, you can evaluate distance, define some metric to evaluate distance between particle pairs, okay? And then you find the closest two particles in this metric, invert them. And then you keep repeating the process. And then you repeat until the stopping condition, which are typically two types. One is called inclusive jet finding, jet clustering. One is called exclusive jet. So in one case, we keep doing this until the minimum distance between particles are large enough, and we stop. And in the other case, in some simpler systems, we can do exclusive, which is we repeat until there's one particle left. Right? For example, if we know that there are two jets, we can repeat until there are two. Yeah. And both have advantages and disadvantages, depending on what you want to study. Okay, so this is a visual explanation, example of how it looks. So in this case, each circle is a particle. Okay, and the size of the circle is the momentum. So suppose that we have this set of particles in the beginning, and then in each step we find the closest two. In this case, these two, and we merge them. Okay, and then we continue doing this. In the next step, it's these two, and we merge them. And we keep doing this. And in this case, it's an inclusive clustering. So we stop until the distance, minimum distance is large enough. And in this case, we found 4 jets. And we can go back in time and see which one this is made of. And we will have jets and constituents, particles that are made of. Okay, so this is how the algorithm goes. And there is a specific family of algorithm, which is the KT family of algorithm, where you define the distance measure like this. So there's the angular term. So this is the angular open angle between the particles times a PT weighting term. And this P is a free parameter that you can use. So different P give you slightly different clustering. And for example, P equals 1 is the KT clustering algorithm. P equals 0 is usually called Cambridge-Aachen clustering, where the moment doesn't matter, and you only have the angle. So the cluster is only based on the angular distance between particles and not the momentum. And -1 here, it's called the anti-KT clustering. And another thing is that there is this R0 here, or not. That's called the resolution parameter. So it effectively determines how big the jets are. That's this overall size. Okay, so here are some examples of one collision event with clustered into jets. So on each of these plots, that's the same event. We have particles. And this is by azimuth angle and the rapidity of the particle. And the height is the PT of the particle. Okay, and there are a lot of mini particles that you don't really see here, but it's scattered everywhere. And here's one example of the KT clustering. Each color is one jet. And here is an example of Cambridge-Aachen clustering. And this is the anti-KT clustering. Okay, and basically different clustering algorithms give you different jets. And one thing that was stood out is that if you look at anti-KT algorithm, everything is very round, which is a very nice property to have. And that's also, so most of the recent, at least LHC measurements are gravitating towards anti-KT jets because it has nice properties. But in principle, you can study each of them separately. Okay. And this is code. It's a previous generation clustering that I won't go into here. Okay. Okay, so back to the definition of jets. Because we have a clustering algorithm, the definition of jets becomes depending on the clustering algorithm. Okay. So conceptually, what we tend to want to think is that a jet is everything that originates with high energy quark. Okay, so that's conceptually what we want to think about when using linear order. But practically, it's whatever the algorithm gives us. And these are typically not exactly the same thing. Okay, and so the consequence is that we have different set of jets, and the connection of what this gives us to this picture might be different. So in some cases, the connection will be better. In some cases, the connection will be worse. And so if we want to compare theory and data, then it's necessary to specify what algorithm we're using. Otherwise, we don't know what we're comparing. Okay, so this is how we find it in experiments. And just one more word on the jets detection in detectors. So jets are mostly made up of light hadrons, so mostly pions. It's the lightest, which creates we have the most of it. So pi plus, pi minus, pi zero. But since pi zero decays to 2 photons, so we also have a bunch of photons. So we have pi plus, pi minus photons, and then sometimes some other particles. And if you remember the splitting function, we have self divergence there, the split emission probability. So which means that we naturally get a lot of self particles. Okay. And there's an interesting consequence of this if you put it in experiments, which is that usually we have magnetic field to detect the momentum of the particle. And the magnetic field bends particles. So if the particle is too soft, it will be just circling there, never made it to the first layer of the detector. And so essentially what this means is that naturally we will have a lot of invisible energy in the jets. And depending on detector design, this can range from a few percent to 10%, something in that order. And another consequence is that depending on how the shower develops, the visible jet energy will be different. Okay. And experimentally, this means that we need corrections to fill in the missing parts because we don't see everything. And this is a bit scary to think about. I'm happy to talk more, but for now, let's leave it like this. Okay, so now what do jets look like? Let's look at some basic properties, just to give a mental image of how they look like. First thing, number of particles. Okay, and so this is a measurement by Atlas collaboration for particles, charged particle equivalent of 500 MeV. And the jet range is like 100 GeV here and 100, 500 here. And so what we can learn from here is that we have like 10, 20 particles, somewhere in that order, depending on jet energy. And if you work on cases where we have lower jet energy, then it will be a little bit smaller than this, but something this small. Okay, and what about the momentum of the particles inside the jet? Okay, so for this, we can look at this data, which is the PT of the particle divided by PT of the jet. So what percentage of jet energy is carried by the particle? And we measure this data function. Okay, and this is what we see. So the peak is at few percent. Okay, and the majority is less than 10% or so. So this tells us that we have a lot of soft particles carrying like percent level energy of the jet. Okay, and this is in line with what we know from what we expect from the theory side. So it's all good. Now, how about the shape of the jet? So here we can measure how much momentum is. So we take a look at a jet. We look at the distance to the jet center. And we measure how much momentum is as a function of R. Like how much momentum is within R0 to 0.5, 0.05 to 0.1, and so on. Okay, and we can measure this. And this is the result. This is self-normalized, normalized to 1. Okay. So it's a steeply falling spectrum. And most of the energy is contained within a very small radius. Okay. And if we integrate this up to 0.05, you can see it's about 50% is within 0.05. And by the time you go to 0.1, it's like 75%-ish. Okay. So everything is very concentrated within the center, which is what we expect, right? We have a lot of collinear splittings. Okay, so another thing we can look at is the jet cross-section as a function of radius. So we measure jet cross-section for small jets, and we measure cross-section for large jets, and we take a ratio. Okay, so this will, it's similar to this, but we will quantify in terms of cross-sections. Okay, the result is here. So everything is divided by R in 1.0. That's the biggest. That's a reference. And different colors are different radius. So what we see is that as we increase the radius size, we enclose more energy, and therefore we have a larger cross-section. And even as the largest one, the gray one, so R0.8, the cross-section is still like 90% of 1.0. So things extend quite a bit. So even though most of energy is concentrated, the tail extends to quite far. Okay, so to summarize what we know for jets, how they look like in vacuum, it's concentrated. Energy is concentrated, but there's a tail extending quite a bit. And when we look at permutations, it's mostly soft particles, and it's mostly light hadrons, ions also. And for number of charged particles, it's typically 10, 20 of them. And if you have low energy, then it's lower. Okay. All right, so that's how it looks like in vacuum. I think it's a good point. Any questions for now? Yes.
In when you reconstruct the jet, like for the sequential recombination algorithm, where you like have everything in a certain position? Is that like momentum space?
It depends on your distance measure. So
Okay.
it's whatever space your distance metric is defined in.
Okay. So it's just whatever you want.
Yeah, as long as it's a metric. Okay, so for the rest of the time, I will talk a little bit about what we can use JET to study. And the first example is to see what happens to jets in MBS and see what we can learn about quantum plasma. And then we'll move on to other cases. Okay, so when we have heavy ion collisions, the shower will develop inside the quantum plasma. Okay. So instead of just splitting by itself, we put it in a liquid and then it develops inside the liquid. And there's a key difference to no quantum plasma cases that space-time structure is not important. We cannot just stay in one space and calculate everything. We really need space and time because the temperature is rapidly dropping as a function of time. The things will change. And this is an example of how it looks like in actual collision. So this is the eta phi space. So this is a Hall detector. And the height is the momentum of each location. So we can see clearly that there is a jet here. It's a concentrated, and there is probably a jet here. There's a concentrated energy here. But in addition to that, there is also a lot of random energies from everywhere. And those are from decay products from quantum that we talked about yesterday. So all these random things that's doing everywhere. Okay, and so the presence of this makes the definition of jets a little bit more complicated than in the vacuum case. So let's talk a little bit more about that. So if we just run blindly with the same algorithms, we just clutter everything, we will have a lot of unrelated energy from the decay of the quantum plasma, which is usually not what we want to study. Sometimes yes, but usually not. And the current paradigm, is that we want to somehow remove them from the jets. Okay, is it for good or bad? We can debate, but that's how people currently do it. And this becomes a little bit tricky for complex. So when we go to jet substructure, then it gets a bit tricky to define things, but we can do it. And one way I like to define it is that it's the net effect of high energy particle. That's one good definition, I think, for jets. Okay. So what this means is that suppose we have some quantum plasma in the case, and then we have the same quantum plasma plus a high energy particle, and then it evolves. And whatever the difference between these two scenarios is the jet. Okay, so to illustrate this, we can think about bowling pins and bowling balls. So this is quantum plasma. This is the high energy particle that we added. So we have two scenarios. One, we have just have the pins, the QGP, and one we have pin and the high particle. Okay. So after collision, some of the pin will be knocked out. Right. So, and the jet remains the difference between the top and the bottom. Okay. And if we do a subtraction, we can see that the difference is actually this plus what's knocked out minus whatever is being knocked out that was there. That's not there anymore. And this is, I think, a functional definition of what most people are measuring at the moment, which is a jet is the difference between the two scenarios. And in this case, it's this plus this minus this. So you can see that it started quickly becomes more and more complicated as you look at different things. So, okay, so again, back to the definition of jets. So similar to the vacuum case, jets in heavy ion is also defined by algorithms. And in the current paradigm, the part of quantum plasma that happens to be inside a jet is not part of a jet. And we need some sort of background subtraction algorithm to take them out. And for the measurements right now, the subtraction algorithm is not part of the jet definition, unlike the clustering algorithm. That's just how people currently choose to do it. In the future, it may change. We will see, but this is what it is right now. Okay, great. So now what do we know about them? Like how do they look like? The first thing we know is that jets are suppressed after going through quark-gluon plasma. Okay, so we can measure the cross-section in heavy ion collisions, and then we can measure the cross-section in reference collisions, typically proton-proton, and then we see how much the cross-section changes. And what we see is that unlike the lepton or photon case, there's a strong suppression. And up here for TeV jets, it's like 0.6, 0.7. So it's quite a striking effect. And this is very interesting because if you look at TeV, it's 10 to the 6 MeV. And the temperature of the quark-gluon plasma is only a few hundred MeV. Okay. So there's a factor of 1,000 difference, but yet a third of them disappeared somehow. Okay. And this is what we call the jet quenching effect. So we see less energy after going through quark-gluon plasma. And we can also go one step further to determine if they actually lose energy or if they just disappear. And to do this is to look at photon jets or jet events. Okay, so before quark-gluon plasma, the momentum will be roughly balanced. And afterwards, this part doesn't matter, it's electroweak, but this part will get modified. And if we look at the momentum ratio between jet and photon Z, we can establish if the energy is lost or not, or if they just disappear. Okay, and the result is that jets lose energy. So if you look at the heavy ion case in blue versus the reference case, we can see clearly that the mean changes to the left. So and this demonstrates that some energy is lost after going to quark-gluon plasma. And we can estimate this is like 10-20%, around that ballpark. Okay, and we can also take a look at particle distribution inside the jets. So this is essentially the fragmentation function. So the distribution of the momentum of the particles inside the jets. So here we plot this Xi, which is, if you flip over, that's the zeta before. Okay, so 0 means that the particles carry 100% of the jet momentum. 1 means that it carries 37%, and so on and so forth. Okay, so soft particles on the right, hard particles on the left. And what we see here is that the reference, the red one, is what we just saw in vacuum case. And the blue one is what happens in heavy ion collisions. So we see a lot more soft particles here, which is quite interesting. And there's also a relative suppression of the high particles inside the jet. Okay. So the high momentum ones are converted into soft, low momentum ones somehow. And the other thing we can look at is radial distribution, as before. So how much momentum is concentrated as a function of R. So here, we also see some differences. So the red here is what we see before for the reference proton-proton case. And the blue one is the measurement from Leset. So first of all, it doesn't change that much. But if we look at the tail region, this log scale, we see that the tail of the jet gets a lot bigger. So energy is a bit less concentrated after going through the quark plasma. So before it was a tight spray of particles. Afterwards, there are a little bit more in the outside, the jet. And this also tells us that energy is pushed away from the center of the jet. Okay. Okay, so to summarize what happened, essentially is that so the whole thing is evolving inside quark-gluon plasma, and there's interaction with the quark-gluon plasma all throughout. And the energy is transported away from the jets. And this causes the energy be captured by the close-grain algorithm to be smaller. And that's what we call the jet quenching effect. And it's kind of like the ripple going away from the duct. Okay. Okay. So that's all I want to say about how jets look like in heavy ion collisions. Now, let's move on to the next part, which is we can also use jets as a tool to study different things. Okay. And the main thing about this is the observation that particles are not uniform inside a jet. Okay. And from how things distribute inside a jet, we can learn a lot about how the shower develops. Okay, so one example is that we can imagine that we can trace through the shower history. So suppose in the beginning we have one particle, at some point it's split into two, and then at some point split into three. Okay. And under some clustering algorithm, we can map them into clusters of particles in the final state. This corresponds to this corresponds to this. And in reality, the correspondence is not 100%. If you look at the correlation, it's not too tight, but it's doable for this. For this is a little bit harder, but at least for this part is, I think it's doable. Okay, and now we can ask the question is, for this case, when they interact with something else, do they interact as a group or do they interact as two particles, for example? And so on and so forth. And let's focus on this case. And as usual, let's immerse it into the quark plasma to see what happens. And the idea here is that we are using the QGP to probe this showering process. And so if the two things are too close to each other, it's essentially one object. So the quark plasma will see it as one object, so one color object. But when they are far away, you will see it as two objects and they will interact independently. Okay. And people went and measured things. For example, this is the opening angle. The RG is the opening angle. Theta G is scaled opening angle. And what we see is that jets with large angle, we see less of them compared to jets with small angle after quark plasma. Okay, so this seems to support the idea that when things are far away, the quark plasma see them as two things. So they lose more energy. But when they are close by, seems to be losing less energy because they are just to the liquid, just one thing. Okay. However, there's no clear turning point. It's smooth. And also it's a little bit paradoxical if you think about it, based on what we know, because we know that tail is enhanced, but we see less large angle structure. So there's something interesting here happening here. Okay, and another honorable mention is the so-called jet energy correlator, where we can use jets to study different things. And this is an old idea from quite some time ago, but recent few years, there's really good interest in measuring this again, okay, in jets. And the energy correlator essentially is, suppose you have a particle, a jet with a lot of particles. Each particle has a distance, and you add up you count how many pairs are at given distance to each other. And then you add it up weighting by the energy. Okay, so that's the energy correlator. And the good thing about this is that because this is separated by angular scale, the different regions will have different dominant physics. So here's one example from CMS. And this is the opening angle of the pair. And down here, when things are very close to each other, it's dominated by hadronization effects. That's, they say free hadron, but it's dominated by hadronization effects. And when you have large angle, it's dominated by perturbative effects. So that's where the proton shower is most dominant. And then there's the transition region, kind of the onset confinement. And in addition to study different physics in different places separately, we can also take this and measure interesting things. For example, from this slope between the 2-particle and 3-particle correlation, you can measure alpha S. And you can also use this for quark-gluon plasma effects and so on. Okay, and I won't go too much into detail here, but there's a lot we can probe with this. Okay, so for the final few minutes, I want to say a few words on what we can use jets to learn in EIC, because there's also a lot we can do here. So as we know, jets are proxies to quarks and gluons. And actually, it's a very important tool in EIC as well. Okay, and because every time you have a quark final state, you have jets. Yeah. And so there are many reasons. Let's go through a few of them. So first one is that you can do precision QCD tests. Okay, so the EIC is a very clean environment to study things in. So it's essentially in vacuum, and you have very good control of the interstate. And this you can compare with PP collisions where it's a little messy. For example, we have the convolution of PDFs, and we also don't really have longitudinal control. So we don't know where the center of mass frame is. We only know the phi direction. And there are also some ISR and MPI effects in proton polar collision. But in EIC, a lot of these are not there. And also we see everything, so we can reconstruct the whole event, which is nice. Okay, so we can perform some precision measurements here. Great. We can also use it to probe cold nuclear effects. For example, when jets are created, it can interact with the cold nuclear matter, the nucleus, and this can cause some energy loss. And in EIC, we can study this in great detail. So as an example, for example, if you look at the cross-section difference from this effect, you can see that for different radius, you see different things. The different radius capture different amount of modification. And we can also look at the chart. Okay. And it's also important in studying for the PDFs. So as for example, as usual, we have the collinear PDFs that we always talk about. But we can also do more. For example, we can study holistic dependent PDFs with it. So you have spin, the polarized spin, beam, and collide, and then you can study holistic dependent things. And also the transverse momentum dependent things. And so on. There's a lot more. And I'm sure you hear a lot about these already. So let's leave it like here. Let's go here. And finally, there's something I found very cool is that you can look into the jets. Okay. And there's a lot of information to learn from inside the jet. And here's one example. So for example, you can look at the hadron in jet azimuthal asymmetry. So the idea here is that you have a jet, you have a hadron here, and you can look at the azimuth angle around the jet axis. Okay. And when you have a polarized beam with in here, then this interaction will cause asymmetry in this direction. And by measuring this asymmetry, we can go back to the polarized quark. Okay, and this is very cool. So, and this is a projection of how well we can do. So this is some calculation, and this is the size of uncertainty expected for EIC. So we can pin this down very nicely. And this is just one example of what we can learn from inside the jets. There are more. Okay, and so concludes. Jets essentially are highly virtual partons showering into a bunch of particles. And experimentally, they are proxies for partons. Okay. And typically, what we see is that we have a bunch of particles concentrated in small area and a lot of soap particles. Okay, so going to hot QCD side, we have the jet quenching effect, which is energy gets pushed away from the center of the jet. And we can study the quark-gluon plasma this way. And one important point is that it's not a point-like object. So if you measure J side, then you have forward momentum, maybe, and not that much, maybe the decay angle, but not that much. But jets are complicated, and there's a lot of things we can learn from it. And it's a gold mine if you think about it. And It's a very useful tool to study both hot and cold QCD that people have been looking at. Okay. And yeah, that's it. Any questions?
Questions and comments? No, what's the typical, or at least is the electrolyte ladder? Then you reconstruct the jets. Is it challenging?
It's up to 15-20, I think,
15-20.
total. So charge will be a bit like thirds, like that.
Does it represent any additional challenges in constructing jets?
Yeah, I think 15-20 is still reasonable that we can do it. But yes, when the multiplicity gets too low, then it gets challenging as well.
What do you do when two different algorithms give you a different number of jets? For example,
For practical reasons, you can think of them as separate objects. So there's jet with anti-KT and jet with KT, for example, and they don't have to match a priori, even though so there's no reason to require jets from different algorithms to match perfectly. And as long as on the theory side, you apply the same thing and they each agree, then that's okay.
Thank you very much. Thank you. Half an hour break. It's good.